Hi, my name is Micheline Harris. I come from a acquisition, actually, from Microsoft acquiring Revolution Analytics. I used R from a very long time, and now I'm moving into the Python realm, hence my Twitter handle, rheartpython. And I'm now part of Microsoft in commercial software engineering.
Excellent. And I'm from New Zealand, which is the birthplace of Revolution R, out of the University of Auckland. So we were just discussing 2 degrees of separation already. And I work as a software engineer across Asia. And we've been here this week together working on an open hack for computer vision and machine learning. And one of the things that came up during the presentation was there's this idea around what is machine learning, what is deep learning, and how do these concepts all come together. And I spent a bit of time demystifying this concept and sharing it amongst the group that I was working within. And we thought it would be great to bring it to the studio to share with more people and all of you out here. So where we start, I studied computer vision at university 20 years ago, and things in computer vision were quite different back then. They weren't necessarily what we have today, but there were a lot of concepts and things that were quite similar. And so when we think about computer vision, there really is 4 main areas that we approach. The first one being image classification. This is there a deer in the image? If you've seen Silicon Valley, you'll know hot dog, not hot dog, that concept. And this is where the computer is determining if a particular object exists within a photo, within an image. Object detection, it's the where is the deer in the image. So it's not just is it here, can you find it, can you put a box around it? Image segmentation, where exactly is the deer? What are the pixels? And this is the tight outline around that particular object that we've identified. And then image similarity, which images are similar to the query image? So you may have seen examples where we do an image search in Bing and it does a reverse lookup, or it uses a photo to find other similar type images.
Yeah, that's actually one of our cognitive services. It's a Bing image search. I love using that.
And the landmark search as well, where you can look at a building and get the response back too.
Yeah.
And so when we talk about AI, machine learning, deep learning, the way I like to think about it is traditional supervised machine learning really has a domain expert or a data science or a person involved that has an expertise in the field. So they look for the elements that are important, and they call these the features, and they extract these and they put weights and preferences on them, and then they put them through some form of algorithm to classify to come out with the answer. So in this example, is there a dog? It would go through this traditional approach of what's the features important to determine a dog, and then the outcome would be yes, no, it is, it isn't.
That's actually like a really nice introduction, because we all know we can't do data science without data, and also data in large quantities is very helpful. So the data scientist can spend a lot of time working with the data, and that can actually end up being quite fun to do too.
Absolutely.
Yeah.
And then deep networks, this concept of deep learning or neural networks, they have this concept of convolutional neural networks, which is really where there's different steps inside a network that determine and do the feature extraction and classification themselves. So a person isn't involved. The network itself is determining aspects of the image, aspects of the picture, and then at the end it brings it back together to answer the question that you posed of it, was is this a dog, or is it a cat, or is it a car? Right. And that's called the connected layers at the end, where it brings the information back. So if we wanted to see an example of this, this would be a deep neural network for computer vision. And the first, the outcome is it a cat, is it a dog, is it a car? It's actually got the answer wrong, because that's my dog Lottie and it's saying it's a cat. So let's not focus on the accuracy of this particular neural network. And here are the convolutional layers that we talked about. And the first stage of the network is really around finding the low-level features. So these are the things that are quite obvious. So it could be the edges of the image, the lines, specific colors, the obvious patterns and things that you find in the image.
Yeah, I like to point out you have a lovely diagram with a it's almost like a flashlight is being shown on the image, and each flashlight is like a filter,
Yes,
right?
yes.
And we have these filters, and the filters are like these parts that recognize like the patterns, right?
Yeah.
Something like that, yeah.
And then the next stage, the high-level features. So this is things like corners, simple shapes, circles, contours that you might see. And these are things that stand out, not just within the image itself, the whole image. It could be components of the image. So it could be a section of the image has some of these features within it. And then the next stage, and as we get deeper into the network, it's really around parts of the image. So it's finding faces, it's finding windows, it's finding wheels, it's finding these kind of common aspects of the images that we have.
Right.
And once it's done all of this work, it kind of works a bit like the brain, where each of the independent neurons is solving a different part of the problem.
Right.
And then it's bringing back all of that information together at these final layers or these connected layers, where it's parsing all of those using some kind of activation function that can bring it into a single view to solve a more complicated problem, such as, is it a dog, or is it a sunset, or some other particular photo. So the complex objects are really the scenes of things like people, animals, beaches, the things that we understand at this human level, based on all of this work that's gone before it.
And I encourage the listeners to, if you hear a term that you don't recognize or that's new to you, don't worry. Like this is the high-level primer.
Absolutely.
And you can explore that term later on your own or in future videos.
And although I called it a convolutional neural network, you'll probably only see it referred to as a CNN. And people will start talking about CNNs. Yeah. And at that stage, that's what this actually means, convolutional neural network. And this idea of using a pre-trained convolutional neural network as a featureizer, this is a concept which we call transfer learning, whereas you've got these pre-built informations from a general task. So this could be a massive amount of images that the network is trained on and spent a lot of time learning about. And then you've got the output layer, which defines, are you looking for a dog in the image? And you may want to solve a different problem. So you might, instead of wanting to define a dog, you might want to say, is this a deer? And this network hasn't been trained to identify deers, and it's never seen a deer before. So using the approaches of a pre-trained network, you could actually say, take off the output layer, which used to define whether it was a cat or a dog, and actually replace that with a new layer which can look and identify deer. So this is really outputs of the penultimate layer. We call it the penultimate layer because it's the second to last layer in the network. I think there's other terms like, what is it, the bootstrap? Bootstrap terms as well. Right. And with transfer learning, the models can achieve, with thousands of labeled images instead of millions. So you might train your original network with millions of photos, but you can take all of the benefit of that work and you can just train it with a few thousand images to refactor the solution. Yeah,
we even have cognitive services that are built on transfer learning, right?
Custom Vision AI.
Custom Vision AI. Yeah. You only have to provide about 30 to 50 images to that because it uses exactly that concept.
And if you do use Custom Vision AI, you'll notice there's a question which says, which is the base model you want to use? And it doesn't use it in those terms. It says, is this a general image problem? Is this a food image problem? Is this a landscape image problem? Yeah. And that's because those are the base models they're talking from, like ones that have been trained in those particular data sets.
Right.
And so therefore, if your problem is similar to those, it may offer better results. And then there's a new output layer which is created, which is now, is it a deer? And so that there in itself, as you're training one or more layers of the network, you're not retraining the whole network. So it may take 8 hours, 10 hours to train the original neural net. It may only take 15 minutes to retrain with a new problem space. Yeah. And you may wonder, where do these pre-trained networks come from? Well, there's a site called ImageNet, which is really the world's largest collection of labeled images. It's millions and millions of labeled images defining a whole range of different topics. It's come from Stanford University.
Yeah.
And so here's an example here, looking inside the person area of ImageNet and finding leaders. And then within leaders, there's different types of leaders, spiritual leaders, military leaders, and then examples of each one of those. So it's a massive data set with a whole bunch of context assigned within it. And so when you see image classification, a lot of it comes from this particular data set or trainings across this particular data set.
Yeah, there are actually a lot of sort of competitions, right?
Yes.
Yearly competitions that occur amongst worldwide universities, companies, etc., to do better and better on this ImageNet data set.
Absolutely. So one of the grand competitions is this ImageNet Large-Scale Visual Recognition Challenge, also known as ILSVRC for short.
Yeah.
Now, this started in 2012. Yeah. And the winner, I don't know if it started in 2012, but that's where I'm going to start the conversation.
It did. Yeah, you're right.
And back then, the idea of a deep neural network was really about 8 layers deep. So we talk about these hidden layers being in the middle of the neural network. The solution that won in 2012 was AlexNet, named after its founder.
Yeah.
And it was an 8-layer convolutional neural network. In 2014, you see we move up to 19 layers for VGG.
Yeah.
And then also in 2014, GoogleNet came out and took out a number of categories in the competition using its 22-layer network. Wow. But the difference with the GoogleNet solution is it was kind of like Inception, which became the name of their future networks,
right,
where it looked back into itself recursively at stages through the process as well. So it had that self feedback loop.
Yeah.
And then in 2015, Microsoft Research took out the competition with ResNet, which was 152 hidden layer convolutional neural network.
And this was even in the computer vision space.
In the computer vision space, absolutely. And this came out of the research team in China, in Beijing.
Great.
And when I read an interview with the researcher who was involved in this process, he said at the time all the common thinking was that a neural network couldn't go too deep because each of the filters would get to a point where it was like faint. The feedback from the neurons became too faint.
Error feeding back, and then the parameter space is right.
And it would be impossible to actually bring it all back at those output layers to have a good result. Mm-hmm. And the techniques that they used kind of proved that that wasn't the case, and that became the new benchmark on how to do image recognition in 2015.
Yeah.
And so, unfortunately, ILSVRC is no more. I think the 2017 competition was the last, and they're moving that over onto Cagle. But the domain has moved a little bit more into this area of COCO. So Microsoft COCO is Common Objects in Context. And this is more of a segmentation challenge than a classification challenge. Mm-hmm. So in this example, in this data set, you'll notice that I'm looking for people and dogs, and it's identifying images which have a person and a dog in it, and the exact pixels of where that person and dog is located.
Right.
And so in 2016, Google took out the COCO challenge using a combination of Inception, which was their engine, and Microsoft ResNet. Mm-hmm. So they call it Inception ResNet V2.
So it's an ensemble.
An ensemble of multiple neural network solutions.
Wow.
Yeah. And this little diagram on the right is just a visualization of the Inception ResNet V2.
Wow.
And when you sort of see this over time, this is building up to the Google COCO 2016, you'll notice the progress that's been made in a very short period of time. This is on the left here, it's like August 2016, up until this was near the end of 2016 when they achieved this. And you look here, the previous winner was Microsoft Research best in 2015 with a ResNet-based solution. So there's a movement now towards this idea of multiple neural networks actually feeding back into themselves, because we're almost hitting the limit of what the individual neural networks can achieve. So it makes sense to then increase the neural nets.
Right, the ensemble learning.
Yeah, the ensemble, sorry.
Sure. Wow.
And this technique is being used in a number of places. So Cagle.com is a website for crowdsourcing solutions for machine learning and data science. And the Cagle Data Science Bowl 2017 was a challenge from a series of photos to determine whether a patient has lung cancer or not. And the winning solution was actually a transfer learning solution that used the Microsoft ResNet.
Oh, wow.
CNN. And it took a ResNet that was trained off a general image data set from ImageNet, and it stripped off the penultimate layer. It then used Microsoft Cognitive Toolkit to retrain the model and retrain the penultimate layer with the K-batch of images. And that took 53 minutes. And then it used a product called LightGBM to extract the features for the final stage and submit that as the solution to the problem. So in less than an hour, using the Azure solution, they were able to apply transfer learning and win the competition for detecting if the patient had lung cancer or not.
Some classification. That's interesting. That's almost like another ensemble.
Yes, it is.
There we go. a lot of this type of learning.
And we've talked a lot about deep convolutional neural networks in this focus, because the focus of the hack was computer vision and the focus of this content is computer vision. But there are other, and also CNNs are used for, like we use it inside a Skype translator. So it's not just vision tasks, but what tends to happen is in other complicated domains, we will turn the data into image data to use a CNN, even if it's not an image problem.
They do this with sound as well.
Yes. Yeah, which is crazy when you think about it. Like if you're trying to determine which is the shorter queue in the supermarket, I know, let's turn it into images and put it in a CNN.
Yeah. Why not? Why not?
But there are other neural networks that are used for other tasks. So recurrent neural network for natural language processing is very strong. Deep belief neural networks for speech and music, and deep reinforcement learning for things like gamification and determining reward is quite common in the gaming environment for determining user behavior.
Wow.
And then, CNNs are everywhere. We have at Microsoft Cognitive Services Face API, which is a service that identifies people from elements of their face, fingerprint in their face, and then can determine things like estimated age and gender, and that is using a trained CNN to perform that task.
Yeah. You can even discover if people are wearing glasses or not with that.
Yes, yeah.
Anyway.
And you see them everywhere. I mean, you see them in Facebook, you see them in image search, lots of different places. And we talked a little bit about custom vision AI. This is just a demonstration of what it's actually doing. It's taking the custom vision model as the classifier in the cloud, and then it's effectively retraining that. So you don't need a lot of experience in computer vision or deep learning to use the solution. You essentially just need to retrain it and then extract or publish that model. One thing I would say is that it's actually really important if you're using custom vision AI to understand about preparation for your image data. Like it's tempting for people to take a really high resolution photo at 3 megabits and then upload it to the service endpoint.
Yeah.
But really for this to work, it's better to have consistently sized images and normalized images when you actually create your model originally, and then performing the same pre-processing steps when you actually upload those images to the service, because a lot of engineers that get involved in this don't have that concept, and then they come back and say, well, the model's not very effective.
Yeah, that's actually a really good point. They even, in the documentation, have a great blurb on that, but the concept of a representative data set, but also the model will not be able to do well on things that it really hasn't seen and been trained on.
Yes.
So it's actually, that's a really good point.
And we as humans are the higher resolution, the sharper the image, the better, right?
Right?
But for a computer, it's like there's too much information in a high detailed image, and it's finding too much in those pixels, and so it really needs to refine it and reduce it. And before deep learning, I mean, I mentioned 20 years ago I was doing some study in this area, and there are a lot of traditional approaches that have been used that are still really relevant today. So some problems don't require a neural net, and they may not come up with the best solutions. Things like very fast OpenCV or SVM classifiers still are very good for determining handwriting in digits and things like that.
Sure.
So just because there's a new kid in town doesn't mean it's the right tool for everything. There are still times when you might use some of the traditional approaches.
Absolutely. Yeah.
Excellent. So I hope you enjoyed the primer, and we'll put some show notes together with some additional links to learn more and to go deeper in some of the concepts. And as Michelin's saying, there's going to be more videos to come as well. And just before we close off, I thought I'd show you what it looks like inside of a neural net, because we talked a lot about it, but this is an example here where playground.tensorflow.org, you can actually start to solve some computer vision problems, like identifying a particular shape here, by creating a neural net with a number of feature extraction layers at the start, and then you can increase the depth. So I can increase the number of hidden layers that I've got. So in 4, increase the number of neurons, and then having that generate the output. So if I press play here, what that's happening over here is actually training and learning as it goes, and you can see each of the neurons doing their thing, looking for the particular features that they're being trained to do, and you'll see them change over time as I hover over them, as it starts to try and solve this problem of getting this shape up over here.
Yeah, this is an excellent tool to just explore different concepts even of a neural network, a dense neural network, to do classification.
And we didn't talk in this talk about activation functions. There are different types of activation functions that are popular. Right now, tanh seems to be the most popular one that people are using, but there's also reglu and sigmoid as the traditional linear, quite familiar with linear regression and that approach.
Right.
If I change the activation function to relu here, it actually performs in a different way, and you'll see a different process and path through the network.
Yeah.
We can talk about that in later sessions. The other thing, the learning rate. Think of this as if you're looking for, you're being in the snow in a whiteout, and you don't know which way is up or down. So you kind of edge forward a little bit, and then you have to gauge, are you going up or are you going down, to try and find the bottom of the hill. That's what the learning rate's doing. It's really looking around itself, and if it's too big, it might miss the hill. It might step right over it. And if it's too small, it might take too long, because it's working really, really slowly. So that's kind of the way to think what's happening with the learning rate there.
Yeah.
It looks like relu wasn't as good as tanh at solving that particular problem. But we can see that, and we can see the example. And the other thing is it's calculating weight. So what it's really doing is it's looking at a particular feature and determining how important is this particular thing in solving this problem. And as it's calculating and going through, it's either increasing the weight or decreasing the weight, depending on how it feels that is significant to
Those
the problem
steps.
state. Yeah.
Yeah, in the whiteout.
Yeah, absolutely.
The error, yeah.
And just to mess with it, you can actually come in here and you could change those weights. So you could say, actually, you're wrong. I think this neuron is more important. You're saying it's a negative 30%, a negative 0.3. I'm saying it's actually 0.8. And by making a change, you're forcing more of the process through that particular neuron, and over time it may pick that up and say, actually that doesn't look right, and adjust it and take it back, because ultimately it knows better than we do.
Yeah. It's got a lot more matrix calculation going on in its head than I do, for sure.
Absolutely. Excellent. So thanks for the time, and thanks for listening. And as I mentioned before, we'll have some more show notes at the end of the session.
Thank you so much.
Thanks a lot. Bye.